Hello, sir.
Yes, ma'am.
Yeah, I think we can start.
Oh, okay, ma'am. A very good morning, participants. I would like to all the participants for a day 9 session 1 of a AICTE sponsor 2 weeks online faculty development program on emerging trends and challenges in a VLSI missile signal processing for fourth industrial revolution. Welcome you all. It's my pleasure to welcome our today's resource person, Dr. Shaila Subramanian, ex-dean, Walchand College of Engineering, Sangli, Maharashtra. Welcome you, ma'am.
Thank you.
If your actions inspire others to dream more, learn more, do more, become more, you are a leader. I'm saying about the person who is none other than our today's resource person, Dr. Shaila Subramanian. Before going to session, let me see the short intro about our resource person. She completed her MTech from IISc Bangalore in 1975. And she has done her PhD in radiation and hot carrier ECTS in submicron MOS devices from IIT Bombay in 1999. She served at Walchand College of Engineering, Shanghai from 1989. She worked as a resource person for various workshops, short-term courses, guest lectures, expert lectures on an MBA and OBE guidelines at various colleges in Maharashtra. She was deputed by a NPIU for delivering a guidelines on NBA and OBE. She was working as an institute MBA and a NAC coordinator and head of the department and dean academics at the Walchand College of Engineering, Shanghai. She had industry experiences in various capacities like engineer, senior engineer, deputy manager for 4 years in, and also from the 14 years in experiences as a senior engineer in a semiconductor devices and IC manufacturing industries in Pune. Her areas of interest are CMOS VLSI design, digital system engineering, DSP VLSI, CMOS VLSI design, analog VLSI design, testing and testability, and so on. In this way, now I'd like to hand over the session to our resource person. Please, ma'am.
Thank you. Thank you. I'll share the screen. Hello.
Yes, ma'am.
Hello. Yeah. Is it visible?
Yes, ma'am. Visible, ma'am.
Okay. And I am audible also?
Yes, ma'am. Everything.
Okay. Okay. In between, if at all you are not getting my, words, kindly just tap me, because sometimes it so happens that I will go on saying and the things are not received there. So in between, I also will be interacting with you. Thank you very much. So I think today is an information era, and all information is in the form of signal. And we know that signal is a complex quantity which has sine and cosine function. Always we represent as z is equal to some signal as equal to a into e raised to z theta, where if you expand e raised to z theta, then either the cos theta, the true part, real part, and the imaginary part as the sine theta. So a cos theta plus j sine theta. So when we are processing this information, because as we say ICT era, we have to process the signals. So signal processing will require Fourier transform, discrete cosine transform, wavelet transforms, inverse of them, and all that. There are the convolution operations, and convolution operation is
Excuse me,
nothing but.
ma'am.
Hello?
Ma'am, actually, your PPT is not visible, ma'am. Only that folder only visible, ma'am.
Is not, is now? No?
No, ma'am.
Okay.
You can
Okay.
share again, ma'am.
I will stop share and again start sharing.
Oh, okay, ma'am.
So share the screen. Now introduction. Is it?
Yes, ma'am. Visible, ma'am.
Okay. Is it okay now?
Yeah, okay, ma'am.
Okay. ठीक है. So basically, what is the basic operation in all this? It is a MAC operation, multiply accumulate operation, as you know. And information we have to process as it is received, because we would like to see anything in real time. Any match, cricket match taking place in Australia, we would like to see at the same time. So it is a real time processing. So we need anyway, we know that finally at the processor, these are the hardware blocks which will implement these algorithms. So what we need is the faster hardware blocks and basically faster MAC units. So there are two methods we know for, multiplication. It could be, or you can say the transcendental function, because e raised to z theta, which consists of cos theta and sin theta, are the trigonometric functions. And we have to process the signal. It means we have to process these transcendental functions or the trigonometric functions, which can be done either by the Taylor series method, which is iterative. We can implement hardware and software there. But then the accuracy will depend upon how many terms we are taking. And there every time it is again a MAC operation. So we, instead of this, which goes, that is basically a MAC unit, will take long time, because multiplication basically is a complex operation here. Adder is okay, but when you consider multiplication, it is a number of additions there. So multiplication algorithms are there, but implementation of direct multiplier algorithm in hardware takes a lot of time. So there is another way, which is a choric processor, where we can have multiplier-less multiplication, which is very, very important feature of that. So after giving some exposure to the DSP algorithms and how the things can be made faster at the hardware level, so that we have the real-time processing of the signals, we will have some exposure of the choric processor, which is basically, we can say, is implemented in many faster algorithms. So my, I think, topic as such is VLSI signal processing with special reference to choric algorithm. I know your basically FDP is on mixed signal, VLSI design as such. But when we say mixed signal, no doubt any natural signal is going to be analog. But finally, when it comes to the execution at a faster rate, at the speed, then you have to work in the digital domain. And hence we have to have the analog signal quantized and then discretized and converted into digital form. And then we do the processing. So finally, the processing is in the digital form. And hence my things will be DSP, the digital signal processing, and the processor which we are considering is also, will take the input in the digital form. But then this digital output again will be converted from D to A converter, which will go in the to the equipments or the systems as such. So though your FDP is analog and mixed signal, this very well is, you can say, the heart of that, where the digital processing comes into picture. So let us, I organize it like this. Initially, we have some overview of DSP algorithms, then DSP architectures, technology implementation. As on today, FPGAs, we can do it now, colleges also. And then we'll consider the choric processor, their concept. This will be the part 2. We try to cover as much as possible. So DSP now we know is an mature technology. We don't have to say what are the advantages of it as such. Basically, it is insensitive to the noise, because we always consider the 0-1 level, and the noise basically is absorbed in that, and like analog, it doesn't get affected by this. So with increase, however, we know that now the technology is 35 nanometers, even 80 nanometers, 9 nanometers, and hence there is basically, if digital also is going in the form of analog, we have to consider what is the crosstalk noise. If the 64-bit bus is there, then these parallel lines will talk to interfere their signals with each other and cause a noise there. So it is the interference noise. The signal returns, and then there's a signal return noise. So we have to basically see how these also can be taken into consideration when we are basically having our digital systems. Now, this is basically not a talk of today's lecture as such, but these are the things to be considered in the high-speed digital design. So where the DSP finds an application, these are the various, areas where DSP algorithms in the various forms are implemented. Again, I'll not go into the details of this, otherwise the introduction will take a lot of time. So typical DSP system, as we have said, the signal will be in analog. The output signal also will be in the analog form or the digital form. But now we are going to basically convert it into digital format by means of sample hold, quantizer, ADC and all that. And this is where we'll be working as a DSP system, where we are basically, for today's lecture, we are concerned about. So what is the objective of a DSP system? As we have said, today's demand is maximize the performance by minimizing hardware circuit. Everything we want very small. In VLSI, that is the purpose. VLSI technology comes to help, that you can reduce the area, you can have it handy, portable, battery operated. Also, that is one of the objectives of DSP system. Minimize area. As hardware circuitry, if you reduce, obviously area will get reduced. Maximize the speed of execution, because you want real-time execution. As the samples are coming, they must be processed. So we want higher speeds. But conversely, we want to minimize the power dissipation because we would like to operate it on a battery. Battery once charge should go for days or for hours like that. So we want to reduce the power dissipation. So these are some of the conflicting requirements: minimizing area, increasing speed, and minimizing power dissipation. And of course, in DSP system, there have to be low quantization and round off noise. So typical DSP computations are convolution, correlation, detailed filtering, adaptive filtering, motion estimation, and the various transforms, as you know, FFT, Laplace transform, Z transform, DCT, wavelet transforms, and all that. So convolution is an operation. We know that basically we try to describe another linear time invariant system. The equation which goes into the convolution is this yn, basically the which comes out of this linear time invariant system is xn, the sample, multiply by some convolve with some hn, that is unit impulse response. This again we can put in the form of summation k is equal to minus infinity to infinity xk h n minus k. It means each sample is multiplied by the coefficient and then the summation of those samples is taken. So here a MAC operation, multiply and accumulation operation is there. Detailed filters will be again characterized by unit sample response, HN, frequency response, H e raised to j omega, transform function, HZ, or by difference equations. So if we consider finite impulse response, FIR, or infinite finite impulse response, for infinite it will go from minus infinity to infinity, finite it will go from 0 to infinity. But what we know here, again, there is a coefficient hn minus k, which is multiplied by the incoming sample. So multiply and then sum for the samples, number of samples you want. Correlation also is similar. Correlation is itself, which is autocorrelation, or correlation between two sequences, AN and XN. So here also, again, as you know, again, MAC operation is there. In, digital signal processing, we come across number of times the matrix vector multiplication form. So if I consider n is equal to 4 and I try to write a correlation in this format, then it can be written in the matrix format like this. And then what you see is that there is a matrix multiplication here. These are the inner product computation, which also are required many times in DSP cases. So inner product computation and then summation. So all these things, what we require is the multiply, that is scaling is one of the thing, multiplication, accumulation is addition. Many times we need to rotate the signals, where I think this Cordic processor will come into picture. So computation of transcendental functions like cos, sine, tan, which can be otherwise described by Taylor series, but not recommended for VLSI implementation or hardware implementation. It is okay for writing the codes and the various transform. And we want in real-time processing. So how to map such data processing algorithms onto underlying hardware. Finally, the hardware which is going to do the job, it is at the bottom of entire system while meeting the application constraints of power, performance, area, noise, round off errors, and all that. So solution is VLSI are the keys for successful realization of many diverse applications in hardware. So DSP architecture designs and VLSI technology, these we can say as the keywords as on today for many applications. They will both meet the constraints of low cost also, because it is a mass production. Once it is approved, you can go in the millions devices or those chips. As we know, the case of a mobile chip today, it has become so economical as on today compared to 5 years back because of the cost benefit and the mass production. Low energy consumption, power consumed is less, and they offer the flexibility. So, we had to go for the VLSI. So here the matching between the marriage between the DSP applications, implementations, and VLSI as a technology comes into picture. So let us see what are the DSP architectures. Earlier designs we know were always using microprocessor, which was the von Neumann architecture. It's a stored program concept. You had a ALU, control unit, memory, IO devices. Power consumption was not very serious issue, but hardware was expensive. It was not issue because we were not really doing the real-time processing at that time. We used to store the data and do the processing, but hardware was expensive and flexibility was provided through software. On the contrary, today's designs are highly integrated system on the complete system is on the chip, and it is a fully hardware approach. There are thousands of multipliers and adders because the bit width also is the word width also is going on increasing. So you have to have number of multipliers and adders because DSP, as we say, MAC is the main thing. Energy consumption has become a critical issue today. Performance is always power constraint because when you increase the speed, you dissipate more power. It's like if we walk fast, we'll get tired. Similarly, if we want higher performance with higher speed, then power will get dissipated more. So that is the constraint. So we have to have a basically balance between speed and the power. And flexibility as on today is provided through FPGAs or reconfigurable hardware as such. So previously what it was happening is that if you have a 256 step FIR filter, then you will take one sample, store it, register it, means a storage device, register it, and then do 256 times, there will be the coefficients which will be stored, 256 coefficients, and there will be a MAC operation, but only one adder and one multiplier. So 256 cycles will have to wait here, or you have to wait 256 times the execution time of this hardware unit, and then only the next sample will get inserted. So the speed was very low here. On the contrary, we can have number of registers here, which is we can say we'll be storing the previous samples here, and then all multiplication being done in parallel. The parallelism comes into picture, which is basically the architecture speciality of FPGAs, and then add, no doubt number of adders will be there because one adder will take 2 units at a time, but taking into consideration the multiplier generally will be taking higher execution time, but all multipliers will work in parallel. So there is only one multiplier time coming into picture plus some adders, and then it was possible to adjust the clock cycle so that in one clock cycle 256 step FIR filter output will be out. No doubt there could be some latency, but that latency will be only for the one sample. Then once one sample starts coming out, then it will be a streaming of the data, and then you will not feel that really it is taking this. Everything will be sequentially done. So this is basically the hardware parallelism aspect of FPGAs. The most popular architectures, even in FPGAs or even if you want to implement in hardware, will be the pipeline and parallel processing. Pipeline architecture, what happens here is that data is consumed, that is samples are taken in, they are stored, processed and produced sequentially. So you have a sequential operation. A pipeline is something like operation going sequentially. Of course, there is going to be an intermediate storage and scheduling of the operations. Then the things will be all right. So control resources are required, but they are of moderate size, and there will be adequate performance speed wise. So either you can reduce the clock frequency if at all your system affords that, or you can increase the throughput. So if you reduce the clock frequency, power reduction will take place. If you want to work with a higher frequency, then throughput will be increased. So these are the pipelining advantages. You already have work on, in the processes also there is a fetch the instruction, decode that, and then execute, and then out or store it. So this basically is nothing but a pipelining approach. So if I consider that if I want to implement, say, let me say yn is equal to an xn, an bn are the coefficients, and this input sample is getting multiplied by an, and then bn gets added, and you have the yn. So what will be the hardware implementation of this? Hardware implementation, yn is equal to xn. This should be a multiplier. This is not adder, this is a multiplier. So xn getting multiplied by an. So here it is an xn added with bn, you get yn. So this is a simple and straightforward architecture for implementing this. But if at all I put a delay element here, this is a combinational path. This is a multiplier, suppose Tm. This 15 nanosecond is the execution time of that, and 5 nanoseconds is the execution time of adder. So I will have to restrict the input data rate, not more than 20 nanoseconds. Only after 20 nanoseconds, the next sample will come. It means what I can say, the speed of the hardware implementation here, the speed of the system cannot be greater than 50 megahertz. Instead, now if I use a two-level pipeline architecture, when I say two-level pipeline architecture, there will be n minus one delay elements in the combinational path. So for two-level, it is a one delay element coming in the combinational path. Now what happens here? Xn is the input sample, gets multiplied by an. I'm sorry, kindly consider this as a multiplier sign. So what comes here is an xn. Similar to this, but now there's a delay element. So when the next cycle comes, what is outputted here is the previous samples which was stored. So it will be a n minus 1 xn minus 1. This n also is corresponding to this sample. There will be a I can say LUT here, which will be having these coefficients, and at a particular instant of time, corresponding coefficient is taken into consideration. So what comes here is a previous sample which was multiplied by the previous coefficient and then gets added now here with Bn minus 1. So you have Yn minus 1 coming here. So when Xn is incident on this two-level pipeline structure, what output I get is Yn minus 1. So there is a delay of one latency of one clock cycle, but it is okay because when I'm considering the continuous streaming of the input data, it will start coming after initially one clock cycle delay, continuous output will be coming here. So if at all I have n level pipeline structure, then there will be latency of n minus one clock cycle. But this really doesn't matter when you are working for 1 hour initial 2 or 3 cycles or even 10 cycles. Even if they do not give any output, doesn't matter, that lag always is will be afforded. In contrast to the what is parallel processing architecture, it is data consumed, processed and produced not in sequential manner but in the parallel in each clock cycle. So there is no need of the intermediate storage. The delay elements will be eliminated from here, and there is no need of operation scheduling also. There is a tremendous performance enhancement. If it is n level parallel processing, approximately n times speed will be obtained here. It means you are working it 100 megahertz clock cycle, and if you have 3-level pipeline parallel processing architecture, you will be in a position to take the data at 300 megahertz. So that much speed enhancement will be there. However, a drawback, always when one advantage is there, there is going to be some drawback. It will be expensive in terms of area, because whatever architecture you were using, now you will have be replicated n times. It is n parallel processing. So hardware will be replicated there, and hence it is expensive in terms of area. So let us consider the same example using two-level parallel processing architecture. Now, again, what I'm considering the same is a multiplier and an adder. There are the coefficients here. But however, now what I'm doing is that this hardware is replicated 2 times because I am implementing two-level parallel processing structure. And what is additionally needed here is that you have to have a multiplexer at the input side and demultiplexer at the output side. Multiplexing of the even samples is done to the upper branch, whereas odd samples is done to the lower branch. And that is, you can say x2k, this is even sample, and odd samples x2k plus 1. So what you have now here is that without having delay elements, y2k, which will be x2k multiplied by a2k plus b2k as per the equations what we wanted, and similarly y2k plus 1 also will be x2k plus 1 multiplied by a2k plus 1 plus b2k plus 1. So same equation is followed here. However, hardware is duplicated. Only thing what you have to do is that you have to steer the samples to the corresponding hardware blocks. If it is going to be n parallel structure, then after every n cycles, the samples will be going to the corresponding hardware blocks, and you will have to demultiplex at the output side. So on a common bus, they will be coming sequentially. So this basically is this one. And here now there is going to be, since you will be now working with half the clock frequency, previously it was 100 megahertz, now you can work with 50 megahertz because you are giving enough time for the next sample to come here, during which this will be active. So you can reduce the frequency of the samples the sample rate can be reduced depending upon what level parallel processing you are working. When because clock is the most power hungry, signal in the hardware, in the digital hardware as such, that will consume more power. So if you can reduce, and that is proportional to the frequency as such. So if you frequency of the clock, the power reduction will take place. So this is basically the idea of the parallel structure. The third, approach which is used is a retiming. Retiming is nothing but relocation of the timing units. That is relocation of, I'll try to keep it here. Okay. Relocation of the delay elements. Now consider this is a 3-tap filter. Okay. What is the equation for that? Yn is equal to AXN plus BXN minus 1 plus CXN minus 2. Okay. So this is the thing. Now, again, I'm considering multiplier delay is 20 nanoseconds and adder delay is 10 nanoseconds. So can you just compute what will be the maximum data arrival rate and the data output rate? How much it will be? Just, I think anybody can give the answer, unmute themselves and give the answer. I want to basically shift this here. Okay, okay. Okay, anybody? So now what you can see here is that this sample xn is incident on this multiplier, which has an input as coefficient a. At the same time, the previous sample, that is xn, delayed by one delay unit. So this is xn minus 1 is incident on this multiplier with b as another input operand. And at the same time, there's a third multiplier which has c as one of the operands, and there is one delay element here. So xn minus 2 will be available here, and then this is axn plus b xn minus 1 plus c xn minus 2, and yn is here. So all the multipliers, which basically take more time for the execution, work in parallel at the same time, and hence only one multiplier delay we have to take into consideration. However, there are the two adders because this has to get added and then get added. So this is the combinational path. The longest combinational path is this xn getting multiplier. All multiplications work in parallel, but then goes through two adder units. So this is tm plus 2ta, tm plus 2ta. So 20 plus 20 is 40 nanoseconds is the critical path here. Critical path always is considered as the longest combinational path in any unit, and that basically hampers your sample rate. It will not be possible for you to input any another sample before 40 nanoseconds, because the things are working here. Otherwise the data corruption will take place. It means 40 nanoseconds, it means 25 megahertz will be only the frequency at which you can input the data and at which you can get it out. Now, the main objective of high-speed architectures is how to reduce this. If at all there is a combinational path, how to reduce this critical path, how to reduce this critical path. If you can reduce the critical path, then you can go for increase in this frequency as such, and that is the and DSPs, we need to do that. So what is retiming approach is that how to relocate the delay elements. So without affecting input output character. This is one of the important things, that you can put a delay element. What you will say is that let us put a delay element here so that only one tm plus ta will be there. But this may affect the equation as such. Let us try to see that. So we have to relocate or additionally put the delay elements in such a way that without affecting input output characteristic of the circuit. Let us take into consideration. I already have said here that yn basically is nothing but axn plus bxn plus 1 plus cxn plus 2 minus 2. If I go to yn minus 1, the previous output will be nothing but axn minus 1 plus bxn minus 1 minus 2 plus cxn minus 3. And the previous is yn minus 2 is nothing. So this is the correct equations as per what I want to implement for 3-tap filter. Now let me say, as I have said, I will try to put the delay elements here. One delay element was not there, so I to put it here and put it here. You can find out that now what I get is that this A getting delayed, again delayed, so it is AXN minus 2. B getting delayed here, again delayed here. So it is bxn minus 2. The third here is C, which gets multiplied to xn minus 2 is xn minus 2. So if I try to put the delay element so as to reduce my critical path, that is the combinational path here, what I get here as Y output is not in what is required by my 3-tap filter. So look, putting the additional delay elements here is not correct. I should not change it. So let us try to put it now. I put the delay element here, 2D minus 2. Okay, not here, but the two delays are put in this path. Now what is xn coming here? So it's delayed by 2 after multiplying. So xn minus axn, but it is delayed by 2 delay element. So axn minus 2. Now here it is D. Okay. Here it is getting again 2D. So here what is bxn minus 3? Here 2D plus additional 2D. So it is cxn minus 4. Now what I get here is yn minus 2 here, which is coming out, is axn minus 2 similar to this, plus bxn minus 3 similar to this, plus cxn minus 4 similar to this. So now the input output relationship is not changed. Now where to put these delay elements? There are some algorithms. Actually, I wanted to cover those, but there was some confusion regarding this FDP from two colleges. I think there was some invitation to me, and one college informed it is postponed. So I took this has been postponed. So I'm sorry that in a smaller unit you will be in a position to locate these delay elements where we have to put so that we get the retiming approach. If the hardware is complex, then you have to have some algorithmic approach. I think I will try to send that those PPTs or that material to your coordinator so you can get that. So today, I think you will get the idea of what is retiming approach. So what we have to do is that you have to add the additional delay elements at such places that input-output relationship is not disturbed. The other DSP architecture is unfolding, folding, and systolic array. That's a popular. What is unfolding? Unfolding is similar to, you can say, is parallel processing, whereas folding is similar to pipelining, you can say, but folding gives you area optimization. You fold the things, so the area will get reduced. Unfolding is like unrolling the loop in software, where you write a C program, there is a for I is equal to 1 to n, and then when it goes for the compiler, it unfolds. So similar to, there is an unfolding. It means you have to replicate the your basic hardware and then have the connection in such a way, again you get the same input output relationship. So replicating hardware, it means area will be more but speed will be there. Folding, it means area optimization is there but there will be the additional delay elements, so latency will be there. And systolic array is something we have said that matrix multiplication also is required in number of DSP application. So systolic array implementation will come to our help when we are implementing matrix multiplication or having some inner products. So let us see what is unfolding. As I have said, concept is similar to loop unrolling. It's a like iteration. That is, iteration is a one word which comes in these DSP algorithms where whatever hardware is used, all that hardware, if used once, it is called as the iteration. If it is used two, it is called as a two iteration. So in unfolding, the similar hardware will be used j number of times if unfolding factor is j. So we'll see that. So let me consider again example which will be clear to you. Let me say yn is equal to, this is basically output depending upon the previous output. So recursive. This is a recursive algorithm. So yn is equal to yn minus 9. So 9 time units back, whatever output was there, that gets multiplied by a plus the current input sample xn, n going from 0 to infinity. Now what will be the hardware here? The hardware here you can see is simple because there is a multiplier, so multiplier is there. There's an adder, so adder is there. And now if you concentrate, what is yn here? Yn basically is coming from xn, but what xn getting added with a multiplied yn, but there is 9 delay elements. 9 delay. It means the here yn which is produced here, this yn will get delayed by 9 time units, 9 clock cycles. So here it is yn minus 9 getting multiplied by a. So a yn minus 9 plus xn is nothing but y. So this is the hardware for that, implementing this equation. Now let us consider the two unfolded version. You can have the unfolded depending upon what speed you want. Correspondingly, you can increase this unfolded factor. Here to make it clear, I have used 2. So 2 unfolded. So you have to replicate these 2 times. So there is a adder, multiplier, 2 times it is replicated. Now I just go to the equation and try to see how these 9 delay elements will be splitted into. Again, there is an algorithm, but let us try to understand this. So if I now consider, again, since it is sort of 2-folded algorithm, I will have to have the even samples and the odd samples. So even samples, so y2k coming out here. How it is? Y2k will be equal to ay. Now instead of n, it is 2k minus 9 plus x2k. So n will replace by 2k. How can I write 2k minus 9? I can write ay 2k minus 2 into 5 plus 1. 10 minus 10, this is in bracket. So 10 minus 1 is 9 plus x2k. What is y2k? Is ay 2k plus 1 minus 9. So it becomes minus 8 plus x 2k plus 1. How will I split it into? Ay 2k minus 2 into 4 is 8 plus 2k plus 1. It means these 9 delay elements are, as if through the equation, as I can see, are getting splitted as 5 plus 4. 5, that is, I will have now the connections where on one branch there will be 5 delay elements, whereas on the other branch there will be 4 delay elements. So between these two hardwares, the communication, or there will be, connection will be through these paths with corresponding delay elements, which we have inferring from this type of splitting of the equation. And now you can see is that what is y2k? Y2k is coming here, which is x2k, no doubt x2k is there, plus this y2k plus 1, if you can see, because what we have got is y2k 2 into 5. So it is going through, so 2k plus 1 going through 5 delays, 2k plus 1 going through 5 delays, and then getting multiplied by a, going through 4 delays, so 9 delays, again a, and is, sorry, this is y2k plus 1 is coming. I have to concentrate on y2k. You can see that. I think I'll leave this here. You can see that exactly what we want is obtained here by means of this replicating the hardware. This is unfolding of approach. So this is one of the approach. Again, how this will be, it was so simple here, so we could divide it into 5 and 4. But again, there is some algorithm, which is a basic sort of, I think you can write the code here and then see that if at all it is j folding factor, where j will be more than 2, it will 4, 5, 6, depending upon what the speed you want, then how those delays should be splitted. And there will be, here we are considering a very simple case of one adder and multiplier with 9 delay, but there could be a complex thing where number of hardware units connected through number of delay units. So how to do that? Again, approach is there. So you can have here word parallel or bit parallel architectures also can be developed here. So folding is basically, which is, you can say, reverse of unfolding. Here what we try to do is that we try to minimize the number of functional blocks. When you synthesize the DSP algorithm, the functional blocks, that is adder, will be reduced, multipliers will be reduced. So you definitely will have the area optimization. But then what you have to do is that since one unit will be coming into picture, one functional unit will be coming into picture n number of times, you have to have some control unit or switching, so that, which is control, so that proper input or the proper processed input is correspondingly going to the proper hardware. So let us again consider this. Again, the same example I have taken into consideration. This basically is yn is equal to, it's just the addition, two adders are there. So initially, since adder requires only two operands, so the output here is an plus bn, then plus cn. So we have simply implemented yn is equal to an plus bn plus cn. But there are two adder units. Do we really require two adders? When we do it by hand calculation also, we will add 4 plus 5, 9 plus 7, 16 plus 4, 20, like that. So at a time we go on adding, but to the accumulated sum, we add the next operand. So this is what is done, and that is what we want to achieve in the folding algorithm. So we want to only have one adder, but one adder will at a time take two operands. So initially an and bn will be adder, and that will be stored. So one delay element will come into picture, and next time that delay element, that stored element, that is the output of that delay element, will be acting for the same adder instead of n. So switching will be done at appropriate time to take that stored input as one stored output here as one of the operands here, and at the same time now cn will be the second operand here, and then you will have next time when you take the next sample yn going out. So this basically is the idea of folding, that is reducing the number of functional units so that area optimization will take place, but you need to have the control switching here. Now consider this. This is only one adder, and we want to store the result, so there is a delay element. And now you can see some switching taking place between the two operands here as well as the output here. Let us consider initially. In the zeroth iteration, A0 will be here, B0 will be, this switch will be on this side. So what will be added here is A0 plus B0. Added A0 and B0. Now with the clock, this will be sent here. This will be stored here as A0 plus B0. Now at that time, now this will be, switch will be here, but the output will be y is equal to A0, B0. We wanted C and also here the one clock later, this first output you have to ignore. But when it goes for the first cycle, you can see this switch will come here where the stored A0, B0 will be given here. At the same time, this switch goes here because this is the first cycle, and Cn comes here. So Cn plus A0, B0, here will be A0 plus B0 plus C0. Second cycle comes, this will go here, and as an output, which is A0, B0 plus C0, that is third. So this is how it is going to take place. You can see here, cycle 0 is A0 plus B0. We are not taking any output in that. The first cycle will be left A0 plus B0. Adder top input will be C0, but will not, at the first cycle, the switch will not be connected here. At the second cycle, here it will be A1 plus B1. Adder will be here A1 plus B1, but at the same time, this A0, B0, C0 will go here, and it will continue. So this is how the folding operation will take place. Only thing, again, how to implement this switching, again, you'll have to have rigorous, and it's complicated. Yeah, you need, I mean, again, not as a can do it by visual inspection, but again, algorithmic approach is needed for that. So general DSP programs are much more complex and need algorithmic approach. When we want to basically fold it by j times, it means there will be a switch which will be from j equal to 0 to n minus 1 will be switching to different inputs to give you the outputs, and is used after retiming. Generally, this folding approach, you have to retime first. You have to basically add the delay elements and do the folding approach, because folding also will require additional delays, and throughput is reduced. Silicon area reduction is there, but here throughput is reduced here. As we have said, systolic arrays is used generally for matrix multiplication. And why the name systolic array? Because there is a host processor, and there are the number of processing elements here. One processing, that is, the host will give some output to this processing element. The output of this goes to the second, and like it is a sort of in the rhythmic way this takes place. Generally, you can think of the, what I say is FMAL operation of the 8086, where floating point operations generally are done by the coprocessor. So it's a sort of coprocessor. Host processor will be doing its job, but when such sort of floating point operation is there, it will give it to the coprocessor, and coprocessor will execute that because it takes more time, and then will hand over to the host processor. So it's similar. The concept is similar, but it is cause-systolic array because it is like a blood flow in our heart. The blood pumping out and pumping in into the host processor. So this basically an idea of the systolic arrays. The regularity and modularity features are there. So it's regular, the speeds are regular, and you can, once develop, you can replicate those. For example, let me consider again the case of a 3-type FIR filter where the equation goes as yn is equal to, these are the weights or ABC coefficients, you can say. W0xn plus W1xn minus 1, W2xn minus 2. And this is called as the dependence graph space-time representation of the 3-type filter. You also might have done, all of you, in the DSP as such. Now, what is done here is that the samples x0, x1, x2, x3, x4 are advertised along the column. Okay. And the weights are advertised along the rows. W0, W1, W2. Now let me consider this particular at time, because initially what Y0 will be only X0, W0 is not a tap filter. Only 3 samples are inputted, you will not get the output. So let us consider what Y3 is. Y3 is coming from X1, which gets multiplied by W2. So W2 X1 comes here and gets added with what? This is X2 W1 gets added with X2 W1. So X1 W2 plus X2 W1 plus X3 W0, and this nothing but Y3. So the results will be along the diagonals. The signals will be along the columns, and weights will be along the rows. So this basically is the space representation of this. This needs to be converted into space-time representation. Again, there are some algorithms. I'll not go into the details of this, but this is another way you can very efficiently, implement the inner product operations. Okay. Now consider, after this, these are generally popular hardware algorithms, architectures as such. So what is the implementation technology? We know today 18 or even 5 nanometer technology has come, which optimizes speed, because when the distance gets reduced, obviously the speed increases. Power is one of the important area. Low power is a very, very important aspect as on today in the technology, because so many we are integrating so many functional units, the complete system on chip. And area, of course, with nanometer technology, lower nanometer technology, area is getting reduced. So we have to have the consideration from the customer specification to the architecture level down to physical level. Physical level, it means the transistor level at which goes in the layout as such. So there will be emphasis in reducing signal integrity, noise issues due to place and route of the library components. There's a huge capital and recurring cost. So generally ASIC technology, we are not going to use it. And in India, again, we are still a developing country. It is not possible to have such a large investment and the things become obsolete in 2 years and we cannot throw away. So at present, instead of, we can get it done from what you call is the TSMC, that is Taiwan Semiconductor Manufacturing Company. If at all you have the physical designs which are of this level, you can use the libraries to simulate all those things and have your tape outs, which can be given to the TSMC for manufacturing. But at present, what we can do in our college, we have to think, we can make use of the FPGA technology, that is the programmable logic device technology. And we have basically even this DSP, programmable DSPs are there, where we can have 32 by 32 floating point operation. We can also have a flexibility to increase the word width, and there are the multi-stage pipeline architectures being used here, and MAC operations also are fast. So we can make use of the programmable DSPs, or we can make use of the FPGAs, which is a very, very handy technology and is not very costly. These are, I think, even open source to certain extent, but if at all you want, all tools of that It's not very costly, and we can do it sitting in your room also. This at your home also, you can design the architectures, you can write the codes for that and implement in FPGA. So this has become basically popular at least at the college level, and even for basically having the prototypes. And the EDA tools are from Xilinx, Altera, Atmel. I think already your colleges must be having this, and they go for the functional simulation, post-synthesis simulation, place and route simulation, and then implement also virtually. And you can again test those for all the other things which are required from actual hardware implementation point of view, like signal integrity, crosstalk noise. And once you are, then you can tape out. You can go to the layout level and tape out the things using cadence tools or mentor graphic tools. So I think all of you must be knowing FPGA. So again, I will not go into the details of this. And this is basically economic solution with minimum time to market. If at all some industry wants an immediate solution, which is a bit complex as far as the normal discrete hardware is concerned, or using microcontroller based thing is is not possible. You can have the required, it's a ASIC, that is application specific, but implement in FPGA, and you can deliver that as a product to the industry, where the time to market or time to manufacture is, well, manufacturing is in your lab itself. So justified, this is justified for the tailor-made low power requirement and prototype development. Reconfigurable FPGAs also are there. So these are some of the FPGAs. Again, I will not go to some Ultra, you can see. So why FPGAs? Because they have inherent parallelism. This is one of the speciality of FPGAs, that they exploit the inherent parallelism, which basically is that of a hardware. If you try to do it using software, it will be a sequential processing. The instruction will be taken and executed. But here, it will try to basically execute the parallelism, which is the hardware aspect. So this is basically FPGA has become very popular as such. Okay, and now we go to a processor capable of performing number of scientific computations, and one of these is Cordic processor. Cordic basically is an acronym of coordinate rotation digital computer. So it's a computer, only digital computer. And basically what is obtained by, these are the vectors are rotated here. And since rotation come into picture here, we have these theta coming into picture, where we can go to really find out the trigonometric functions required again for the DSP algorithms. And this basically is a coordinate. So coordinate system can be linear or circular or hyperbolic. So it can work in any of the coordinate systems using only add and shift operation. This is the speciality of that. No multiplier is implemented. Otherwise, if you see the multiplier algorithms also, the number of multiplier algorithms are there, but very difficult to get the required speed. As one cycle operation, multipliers also are there, but then a lot of hardware and the other things will go into play. This is a very simple, and concept wise, I think you can appreciate that. This is preferred choice for low level hardware, generally used in a hand calculator, generally will be using this Cordic for computing use trigonometric functions. Now let us, the operations which can be done are addition, subtraction, no problem. Comparison of two numbers using relational operation, greater or less. So this is possible. Storing and retrieving numbers from memory. So memory unit will be there, and shifting the binary point. We know that in a digital, when we are considering the binary data, shifting by one position to the left multiplies it by 2, whereas shifting, divides it by 2, whereas shifting it to the right multiplies it by 2. For example, let us consider 1011.11. Now, if I take it 2 positions to the left, what I get is 11. What I get here is 10.1111. If you try to find out the value of this is 11.75. Now, if I shift it by 1 position here, it is this binary number, and the value will be just the double of that. So shifting right by 1 position, 2. If I shift it by n position, it will multiply by 2 raised to n. So this basically similar thing is also for the shifting left, that is the divide operation. So let us consider now, this is the vector rotation analytical treatment. So let me consider I have this coordinate geometry, linear coordinate geometry. So I have a vector here, which is xn having coordinates xn and y. I rotate it through angle theta. Initially, it is making an angle beta as such. I rotate it through angle theta. It takes a position which is like this, xr, yr. So m in is basically the length of this. Now, if I try to write the equation for xr and yr using this theta as the rotating angle with initial angle making with x-axis as beta, then I can write xr as m in, which is the modulus of that, cos beta plus theta, which I solve it, expand this, I get as xn, it is in the initial coordinate, in the terms of the initial coordinate, x in cos theta minus y in sin theta. So the vector which was initially at position x and y and having coordinates x and y, after rotating, I have tried to again express it in terms of what? The theta is the angle of rotation and its initial coordinates x and y. Similarly, if I try to find out what is yr, I can write it as m in sine beta plus theta, because yr is this, which is nothing but m in theta plus beta coming into picture, and this is nothing but sine beta plus theta. So again, I solve it, I come to an expression where it is expressed in terms of angle rotation theta and initial. So these are XR and YR, what I'm getting. And this is nothing but I can express it in terms of X in Y in, and this is rho theta is an operator, which is nothing but this matrix cos theta minus sin theta, cos theta. So in the matrix form, I can write that rotated vector coordinates XR, YR in terms of rho theta operator given by this and X in Y in. So what I need to do is that I need to find out the cos theta and sin theta. In if at all I have to find out XR, YR. Or if I know XR, YR, I can, and initial X in Y in, I can get the value of theta. So this is the simple concept in that. If I do it mathematically, I know that there's a relationship between the rotated vector coordinates with the initial coordinates and the angle theta. Or if at all I know these two things, where it has gone, from where, then I can find out theta, or in conversely, I will try to find out this value in and try to put cos theta and sin theta. Once I get sin theta, cos theta, I can get tan theta. So what is done here is that this theta angle, that is the angle of rotation, is being splitted into number of micro rotations. So we take the small rotations here. So we try to, express theta in terms of summation of alpha j, where alpha j is nothing but the small rotation, micro rotation taken. So this rho theta now, that operator now will be the product of j0 to infinity, because I am going to take number of micro rotations. So it will go to number, this theta will get limited to 10 or 12. Finally, you will see a rotation of this alpha j. And then I can express this as the final rotated vectors. That is, after jth iteration, I will have the coordinates xr and yr expressed in terms of the previous j. This is xr j plus 1 in terms of previous xr j and yr j, and in terms of cos and sin instead of theta, now that micro rotation alpha j has come. So the same equation I have now split it into terms of, expressed in terms of the micro rotations. Now, however, what we see is here that is I have got these XR and YR for the next iteration from the previous iterations, but there is cos alpha j, sin alpha j coming into picture. Again, multiplication is there, and then we are saying we are going for multiplier-less processor. How is that? So again, mathematical manipulations here. I am going to take cos alpha j out. So here will be XR j, and the sin alpha j upon cos alpha j will be tan alpha j. So here cos alpha j has been taken out from both the equations, giving you some relationship again in terms of the jth coordinates and tan alpha j. So there are now 4 multipliers, because 1, 2, 3, and 4, and 2 adders are there. Now I am going to do a trick, That is, this basically is. Actually, this algorithm was in some 55s or so, but it got the advantage when this FPGA or this VLSI technology was basically after 95, you can say. So choose this alpha j such that tangent of alpha j is a power of 2. So we know that shifting by a power of 2, either left or right, will eliminate. That is, will only take this float, binary point to the left or right of that, input as such. So choose alpha j in such a way that tangent of alpha j is a power of 2. So tan alpha j has to be either plus or minus. Either rotate it anti-clockwise or clockwise. So plus minus sign has come here as 2 raised to minus j sigma j. And then alpha j will be tan inverse of this, and where this sigma j, that is the sigma j basically is a sign, plus or minus, wrote anti-clockwise or clockwise. So sigma j tan inverse of 2 raised to minus j. Okay, and then what we have is, then we are again trying to express this as, where this will come into picture, that this tan alpha j getting multiplied as yrj. I think this should have come earlier, where there are the 4 multipliers and 2 adders as such. I think this hardware should have gone previously. Anyway, doesn't matter. We got this. So now rotation, the extension scales modulus of mj. So what we have is, if I try to consider only the modulus, that is the length of this, mj plus 1 will be equal to kj mj. That is magnitude of that vector for the jth iteration, multiply by kj, which is cos alpha j was coming into picture there. So mj plus 1 cos alpha j was something. I'm only considering the magnitude part of it. So to that magnitude part, if I divide by cos alpha j, then what I get is that mj plus 1 will be expressed in terms of 1 plus 2 raised to minus 2j under root of that into mj. Again, I think this cos alpha j, 1 upon cos alpha j expressed in terms of sec alpha j expressed in terms of 1 plus tan square of alpha j. And all these simplifications will let us to derive, that is the magnitude of the next rotated vector after micro rotation, mj plus 1 is 1 plus 2 raised to minus 2j under root of that into mj. So there is some relationship between the magnitudes of this. So if I consider now, if I want to add this total scaling factor, it is going to be the multiplication of this factor after each rotation. And each rotation we are considering that rotate in such a way that tan alpha comes in the powers of 2 raised to minus j. And hence, if I try to solve that for j is equal to 0 to infinity, this particular, everything is known, j is going from 0 to infinity, and the product of that, I converge at this factor 1.6468. This is the beauty of this. So I know in advance that finally that constant is going to be 1.6468. So if I initially eliminate that, then my equations will become like this. That is this cos alpha j, if I divide it 1 upon cos alpha j, and then finally if I go on multiplying that magnitude factor, it only comes to a factor of 1.6468. And then if I just keep this aside, so with this scaling factor eliminated from the, this is the scaling factor final, and this is n number of times you can do it, it will converge to this, maybe some 9, 2, 3, something like that will be, but you can very well take it to 1.6468. So now I eliminate that even magnitude part, and I have considered get this equation, choric equation, xj plus 1 is equal to xj minus sigma j 2 raised to minus j yj, and yj plus 1 is yj plus sigma j 2 raised to minus j xj. Now sigma j basically are the signs, plus or minus. Either rotate it in the plus or minus, that depends upon the comparison where we have come, whether we have achieved the targeted value or not. If the achieved value is more than targeted, it is the reverse operation. If less, it is the anti-clockwise operation. So This is the plus and minus is decide the rotation direction. 2 raised to minus j we know is going to be binary point shifting only, and hence it is only add. The subtraction also is a sort of addition only. We consider it in terms of addition. So these are the add and shift operation. So there is no multiplication here. So multiplication has been completely eliminated from the chordic equations, and now implementation of this is the hardware thing. Now we are talking about the choice of the angle. So what we said is that let alpha j should be such, it is tan inverse of sigma j 2 raised to minus j. Sigma is the direction of rotation. So let us try to find out what is 2 raised to minus j. So let us try to find the angles 1 upon 2 raised to n, because 2 raised to minus j is nothing but 1 upon 2 raised to j. So let us try to find out j equal to 0 to some values. So let me consider n equal to 0. It is 1 upon 2 raised to 0, 1. Tan inverse of 1 is 45 degree. So theta 0 is pi by 4, which comes out to be in 0.785398. Okay, this is in radians. The next is 1 upon 2, that is n is equal to 1, half. That angle comes out to be equal to 26.58. In the radians, it will come out to be 0.4636. 1 half is 0.5. Okay, so it is approximately half. If I consider 1 upon 2 raised to 2, it is 4. The angle comes out to be 14.04. Theta 2 is tan inverse of 1 by 4, which comes out to be equal to, in terms of radians, 0.244979, which is very near to 1 by 4. If I consider 2 raised to 3, it is 8. So 1 by 8. So the angle comes out to be 7.12. And you can see as this angle is going on decreasing, my theta value 1 by 8, which is this, is exactly same as the theta. So as theta decreases, tan theta is equal to theta. And I'm going to consider this slowly the decreasing angle only, and I will have number of iterations. And if I go on doing this, finally what I will find is that tan theta is nothing but theta. So whatever, if I consider 1 upon 2 raised to 10, that whatever value I get in radians is same as 1 upon 2 raised to 1024. So instead of storing the values of tan theta, we can store the values of theta itself. So the first rotation will be through 45. Now I'll come to that algorithm I said. So why it has been taken as tan inverse of 2 raised to minus j? Because slowly, as you go on rotating the vector, initially it will be a large vector giving 1 upon 45 degree, then it will be 26 degree and so on. And then you will go on reducing the value of theta till it converges. The rotated vector converges to with a value theta which was targeted by you. So we'll come to that now. So this basically is the concept behind the choice of the angle. So now let me again coming back to the same figure. I have initially, this is my vector x in y in, making some angle. Now this theta beta angle gets eliminated. We have seen in the equations, initial beta was not coming into picture at all. It was only in terms of the rotation angle theta. So from here, now let me say I want to go to this final angle except yf. I want my this initial vector to be taken here to except yf. So this is the theta final I want. But now this theta is splitted into micro rotations. Now micro rotations, in the sense, the first is not micro rotation. It goes in terms of 1 upon 2 raised to n. So initially it will be a 45 degree angle. So 1 upon 2 raised to 0. So from here we go to this. We go to this. So this is the thing which is x1 y1. Now this where it has come is greater than except y. What I wanted is here. So I mean compare that where I have come. Initial was this. So I have come to this, whether it is greater or less than this. If it is greater, then I have to reverse the direction. So I reverse it by 1 upon 2 raised to 1, which is 26.5. So from here, I take a rotation which comes here, which is of 26 degree, 0.5 degree. So I come here. Now this is x2, y2 position, the same vector now having x2, y2 as the coordinate. Now this angle, whatever final angle I have got, is less than or greater than, now it is less than the final value. So I had to take the next rotation, which is by 1 upon 2 raised to 2, what is 17 or whatever it is. So from here, I go to x3 y3. Now it is greater than the final. So I take the reverse and come to, so slowly by micro rotations and rotating that angle and deciding the direction of rotation, I will reach to the converge it to whatever value I want. And once I get that, with the scale factor eliminated from that, this xf gives me cos theta and this yf gives me sine theta. So the coordinates, final coordinates obtained from these choric equations will indirectly give me the sine theta and cos theta. This basically is the concept of choric processor. Sir, are you with me? Hello? Hello? Hello, sir?
Yes, ma'am.
Yes. So is it going okay?
Yes,
Hello?
ma'am.
Hello?
Ma'am.
Yeah,
Ma'am.
is it going okay?
Yes, ma'am. Everything okay, ma'am.
Okay, okay,
You can
ठीक है.
continue, ma'am.
Okay, okay,
Okay,
okay,
ma'am.
okay. So this accumulation of the angle, what we are doing is that Z is the, now previously we had only X and Y. Now we are trying to bring Z into picture. So this Z variable is part of the angle which has not been rotated yet. So this is the remaining part. So if Z plus 1 is whatever is the targeted angle theta minus so far accumulated angles, whatever rotations I have got plus or minus, that I go on adding. If it is a reverse, it is negative. If it in the forward, it will be plus. So this is the unrotated part of the angle. And for every step of rotation, sigma is computed as sine of this Zj. So sigma n is -1 if Zj is less than 0, which is the unrotated part. Hence, so Zj determines whether next time I have to rotate it in the clockwise or in the anti-clockwise rotation. So sigma n is equal to -1 if Zj is less than 0. Zj is unrotated part. It means I have basically rotated it a more angle. So I have to reverse it. So Zj direction will be negative. On the other hand, if it is less, that is sigma n is 1, it means I have to rotate it still further. So Zj will be positive. So Zj plus 1 is equal to theta minus summation of all those micro rotations. And then theta is nothing but summation of sigma j alpha j, where alpha j is, as we have said, tan inverse of 2 raised to minus j. So I get a third choric equation for next rotation. Zj plus 1 is equal to Zj minus theta is nothing but sigma j tan inverse 2 raised to minus j. So now I add the third equation, which are these coordinates x and y, and this is for rotating it further, giving me the direction of the rotations and through how much is by this equation. So these are basically the choric equations for the micro rotations. So you can use in the rotation mode. I'll try to cover the rotation mode, but you can have the vectoring mode also. Here I try to reduce the value of theta here. And the three coordinate system as circular, hyperbolic, and linear coordinate system. So you can have the various entities being outputted when you try to use either one of these modes and one of these three coordinate systems. So let me I'll cover the rotation mode in detail. This algorithm is known as driving Z to 0. So Z is the unrotated part that you are trying to make it to 0. So initially I have some targeted value theta, and I go on doing the micro rotation in such a way that the unrotated part of theta goes to 0. It means I have achieved the targeted value, and the equations to be implemented, as I have said, xj plus 1, ij plus 1, zj plus 1 as given by this, where this k is that modulus which was 1.6468. So this xj, this k can be brought into picture either initially or in the last equation. So if we start with the initial value as x0 is equal to x in equal to 1, let me say initially x in is 1 and y0, yn is equal to 0. That is, I start with x-axis only. Initially, I do not have any y coordinate, value as such. And z0 is theta. So theta is the I want to, because I want to find out sine theta, cos theta. So theta, I know it is 35 degree. So that I give as the input. And decompose the angle using equations these. This I had seen, that is the third equation in the choric. and then perform the micro rotations till algorithm converges to the final value, which is the xf is k into x in cos theta, y in cos theta, that is equal to k cos theta, because this we have seen reduces to k cos theta, and hence cos theta will be nothing but xf upon k. So this k will come into picture. Finally, what value of xf I get, if I divide it by k, I get the cos theta. Or if I start x in is equal to k itself, that is instead of 1, if I start with 1.6468, the k value itself, and y0 is equal to 0 and z0 is equal to theta, then cos theta will be nothing but xf, and sin theta will be nothing but yf from these equations, and zf unrotated angle becomes 0. So if we start rotating the vector with initial values like this, then after doing the micro rotations as per the algorithm of Cordic, when it converges, when I get unrotated angle equal to 0, that is rotated angle is equal to theta, then the final value of the coordinate is nothing but cos theta, and final value of if is nothing but the sin theta, and zf is the unrotated part becomes 0 because you have reached the final value. And here is the same thing explained here, with considering 40° as the angle. We want to go as a 40°. Initially start with x-axis, as x is equal to 1.6468, y equal to 0. So somewhere I am here. Okay, somewhere I am here. Then initial value rotate. So alpha 0 is equal to 0. No rotation. Summation alpha I here, and alpha 0 is plus. These are the column values. So the first iteration I take it through 45°. It has gone here. But the angle, so summation alpha is 0 because initially it was 0. So 45. Now I have exceeded this 40 value. So my direction is -1. So now I go through reverse direction. It goes to V2. But alpha 2 is 26.55. But initially I had gone through 45 and now through 26.5 in the reverse direction. So summation of alpha is 45 minus 26.5 is 18.45. So I have come here. Now, is this value less or greater than required 40? It is less. So direction is plus. So now I have to rotate this in this direction. With what value? 1 upon 2 raised to 2, tan inverse. So that is angle is 14.3. So from 18.45, this I go to 14.03. Now this is added, is 14 plus 14, 18 plus 14 added is 32.48. Still it is less than 40. So the angle of rotation 1. So if I go on doing this back and forth like that, slowly converges to a value where theta is equal to, after 14 rotations, it has gone to 40.003. And now, even you can go to still more accuracy, but this is how a rotation vector in the linear mode will work to give you. And now if I try to find out what is sine theta and cos theta, they will be with an accuracy of 1 upon 2 raised to 14. The 14 rotations I have done, it will be of the which less than 10 ppm. So the accuracy of this method will be within 10 ppm, instead of going through the Taylor series and executing so many times, and depending upon the number of terms you will get accuracy, but the hardware required is more, time of execution is more. This is within 14 iterations, and for processor 14 iterations is nothing, or even if you go to 20 rotations, your accuracy is going to be this one. So, I'm just giving you can have a circular mode, hyperbolic or linear mode. In the rotation mode for the circular, you get cos theta, sin theta as the final value. Theta will be 0. If you go for the vectoring mode, you can get the square roots and tan inverse of theta. I think this again, you can go through the details of codic processor and how to apply it in the vectoring mode for different coordinate systems, and you can get the values of cos. Hyperbolic, you will cos theta, sin theta, and similar to this, it is square root of this, and finding the square root also is a very difficult many times mathematically in using hardware. So that also is done using coprocessor, codic processor. This hyperbolic mode. In the rotation mode, the final value will be x. This will be y plus x theta, and this is rotation mode is always reduced to 0. vectoring mode like this. So you can get different values for this. These are the with what initial values you start and what are the functions executed by that and what you get. So these are the things, functions, summary of the functions using Cordy. So evaluation of the rotation functions more efficient than Mach units. The Cordic will save hardware cost. It implements both parallel and pipeline architecture and generates very high throughput because the number of iterations are very handful. And with the, today's frequency, clock frequency to the processor, I think we can work, or even if it is implemented in FPGAs, it will be very high. So throughput will be high. As a regular aspect is there. What is there is nothing but the shift operations. Now the comparators are there, adders are there. So if you develop these basic units and replication of that, you can get the Cordic processor. The utility of Cordic-based architecture lies in its generality and flexibility. Can be successfully implemented in FPGA, converges in finite number of iterations, and accuracy is of the order of, for n is equal to 20, is of the order of 10 ppm. It is of course, it is an iterative algorithm which only uses add, subtract, and shift operation. No doubt we had to implement the block for doing the comparison to find out the value of targeted angle and the accumulated angle. You can adjust the scale through the gain of the processor, or you can select the initial vectors in such a way that final scaling factors get eliminated. This is one of the speciality of the Cordic processor, that scaling completely gets eliminated by proper choice of the initial vector or the gain of the processor. There are two modes, as we have said, rotation and vectoring, and 3 coordinate systems, and then giving you the different functions. So now robotics is one of the very important field, as and today in the, all systems we are making use of these robotics. I think where the robot has to have many movements, and one of that is the rotation also. So in that also you can think of implementing this. Navigation is another thing. You have to basically navigate. It could be through seats. The ships will be navigating in the proper direction. So there also you can make use of this to find out at what angle you are or where you want to go once you give that targeted thing. You can implement the linear transform. As far as DSP is concerned, we know we can implement the linear transforms, digital filters, solving linear system of algebraic equations to give the solutions. You can use it in digital or image video processing, 3D graphics, robotics, navigation. So these are the very separate. Wherever I think you are thinking of implementing the transcendental functions, I only concentrated on the trigonometric functions, but you can do all sorts of e raised to z theta things. That is the transcendental equation functions. Wherever are there, you can go for implementing Cordic processor. So I summarize the thing. Initially, we started what are the advantage of digital signal processing. The objectives of digital systems being reduce the area, have the speed, that is performance, and power reduction also has to be there. Should take care of the round off noise, and the other noise, interference noise, and all that. And one of the great feature of any DSP computation is nothing but the implementation of the MAC, that is multiply accumulate unit, at the hardware level. And here, I think we say that DSP as a what you can say implementation in VLSI are marrying very nicely with each other, and hence VLSI technology can be very efficiently used and is being used, not is something which will be done, is being used for implementing DSP algorithms for the various applications which I have cited just now. So what are generally the favorite DSP architectures with example of 3-tap FIR filter and some simple equations, DSP equations or mathematical equations, I can say, where I was considering some signal is coming, getting multiplied with some coefficients and then processing it further. So with some equations, we have seen how the pipeline approach can be used by inserting the delay elements in the combinational path, so that critical path delay gets reduced, and you can either increase the clock frequency or you can increase the throughput. Then parallel processing approach is replicating the hardware and streaming the inputs and outputs appropriately.
using multiplexer and duplexers at the input and output side. No doubt area you have to spare there, you have to basically sacrifice on the area, but the sample rate can increase, or if you keep the same sample rate, perhaps what I say is that the power reduction will take place. Retiming is nothing but inserting the delay elements at appropriate position so that again critical path delay is reduced and you have the speed advantage. Unfolding is similar to parallel. You basically replicate the hardware by the unfolding factor and correspondingly give the connections between these unfolded units in such a way that the equations are not altered, they remain the same. Area sacrifice again is there, but again speed advantage or the throughput advantage can be obtained here. Folding is basically folding your architecture. It means you reducing the number of functional blocks. That is, you are going to give a job of number of similar functional blocks to one or two and switching the inputs in such a way that at appropriate time, appropriate functional block with appropriate unit will come into input will come into picture. Folding algorithms are there. And systolic arrays basically very efficiently can do your inner products computations. I haven't gone much into details of the systolic arrays because then each one itself is basically a topic of at least 2 hours by explaining the algorithm which goes into it and working on that. And to all these do all these things in DSP, I have just thrown light on Cordic algorithm. I think we can also just go into the details of programmable DSP and see whether the architecture used there for finding out this areas to Z theta or implementing this MAC or in terms of the theta angle, whether Cordic processor is there. I think this will be interesting thing to see. Perhaps I will also try to see that. So we have seen very nice Cordic fundamentals and very interesting Cordic fundamentals are there, that how you can modify these equations of the rotated vector starting with an initial vector and then go on, doing micro rotation, reducing the angle with some concept in mind from hardware point of view, and reduce the equations only to the shift and add thing, and then implement in hardware to give you the accuracy which is even better than 10 ppm and the hardware architecture of that. Here also you can have bitwise parallel architectures or serial architectures or all that, those things. So to conclude, I can say today's is a digital and high-speed era. We want all real-time applications. We are basically living in an era where we order the thing and the fast food comes within 5 minutes to your table. It's a Maggie era, you can say. Electronic control, of course, has to be there. So it is a multidisciplinary approach. DSP implementation in almost all fields as on today. You think of anything, many things will be, when you go for the implementation, it is digital implementation. And many times it is the data processing. So data is a signal is in the form of theta, I mean e raised to the theta, and hence and the DSP various operations are is a MAC operation, and hence we have to basically implement it using VLSI technology, which is quite fast, smart, power efficient, and real-time processing. FPGA implementation, which we can do in our colleges, and hence the projects can be given to the students based on this. And I mean, lot of advantage, what I can modifications, advancement has taken place in FPGAs. Also, we have better FPGAs both from Xilinx at Mail. With better and better, even DSP blocks are there so that you can make use of those IPs, that is intellectual property blocks there, which will lead you to a simpler job and then implement these things. This is a boon to design and implementation engineers. And there's no problem even if we do not have the manufacturing plants, we can do that. Sorry. We can do the prototype, which will benefit to society. We can develop entrepreneurship in our students, and we can help in making our Bharat Atmanirbhar. Thank you. Any questions? Sir, I have finished.
Thank you, ma'am. Dear participants, if you have any doubts or queries, you can ask now.
Yeah.
Should I stop sharing?
Yes, ma'am, you can stop your sharing, ma'am.
Yeah, so that I can see if any question is there in the chat box.
Yes. Participants, if you have any doubts or queries, you can either post your question in chat box or else unmute yourself and discuss with our resource person.
Kindly ask the questions. It will be interesting to me. I learn from you. Please. Participants, have you understood the basics? I could only give the glimpses. Hello, sir. There doesn't seem to be any questions. Either the thing was not understood or it was very clear to them, perhaps.
Ma'am, I think there is no more queries from participants, it's ma'am.
Okay, okay. ठीक है, sir. ठीक है. I think it was just a sort of thing. If they haven't studied this in detail, perhaps they could relate DSP with VLSI technology and try to take some projects with the undergraduate or postgraduate students. So that basically the things are much in deeper as such. I have covered only the, I can say, what you say, the tip of the snow. It is only was the tip of the snow, but I had tried to give the exposure of the various terms, and perhaps if they have interest, they can interact with me also for getting more things or the material as such. Thank you very much, sir.
Thank you, ma'am. Let me wind up the session, ma'am.
Yeah, okay. Okay, sir. Okay. Thank you. Thank you very much.
When educating the minds of our youth, we must not forget to educate their heart. In this way, I would like to thank our today's resource person, Dr. Shaila Subraman, ex-dean, Walton College of Engineering, Shangli, Maharashtra, for providing a wonderful session on the topic of VLSI for DSB in this STTP. Thank you so much, ma'am.
Thank you very much. Thank you very much for inviting me. And I could deliver in a short time cap without, because I think this I have taught in my college, and I had done some projects also with that. Codic processor, one of my PhD student also has worked with. So there's a lot of scope in this area. And I think students of electronics and computers can be encouraged to take the projects in this area. And I do not know how strong your VLSI labs are, but if you have PGAs in your labs, perhaps the projects can be done. So how far your expertise of the faculty in this VLSI domain and DSP domain, sir?
Thank you, ma'am. Thank you so much, ma'am.
Okay. Thank you very much. So I'm leaving.
Yes, ma'am. You can leave, ma'am. Have a nice day, ma'am.
Okay, thank you very much.
Thank you. Dear participants, the day 9 session 1 attendance and feedback link is posted in chat box. It will be open up to 30 minutes only, so kindly fill it in. While filling the feedback form, kindly select your respective FDP ID. Thank you all. And all the participants are requested to join the afternoon session at 2 p.m. sharply. Thank you.